inkjet printed conformal array antennas, massive MIMO antennas, antennas for CubeSat, reflector antennas and its feed systems, and metasurface antennas. So I heartily welcome you, sir, to take the session now.
Thank you very much, Surajit. I think thanks for your introduction and thanks for inviting me for this talk. Let me share my screen first so I can, share the presentation. And just give you a minute, so that it works.
Sure, sir.
Yeah. Because this is first time I'm using this Google thing. So, do you see my screen or you don't?
No, sir. We can see you, but the screen is not yet shared.
Okay.
There will be a present now option, sir, at the bottom of the bottom of your screen.
Yeah, that's what I'm clicking. It is asking your entire screen. And
yes,
when
sir.
I'm clicking it, it says that you must grant permission in order to screen share. So can't share a screen. So somehow.
So you can share a window also, sir. Means if you select a window option, then that PPT window might be there. It might come.
It is the same problem actually.
Okay.
It is not allowing me to share. Say that this something looks like my university laptop may have some limitations.
Right, maybe
may not allow. So
if you could, sir, share the PDF of the presentation, I can share it from my end also.
Yes, I'm going to forward you
yes,
right away. I think it may be problem. So, okay. Okay, it should be there with you. And you have to download it, of course.
Sure, sir.
Yeah. Did it reach to you? I hope it is speed of light. I should take some minutes, of course. And I do apologize to attendees here, and until this
yes,
technical.
Sir, I got the presentation, so it will take 5 minutes. Dear participant, we need few minutes to download and present it.
Sure. So until then, I will talk to the attendees here. So I engage them. I hope I will not bore them here. You all have a good morning, and of course, it's night time for me, and it was a long day since morning. But I just wanted to chat with you about the research I do in my lab, and of course, considering the growth of wireless communication, 4G and 5G has been on these days. The lots, new development. Hello?
Hello? Yes, Raghavan, sir, you can.
Till he downloads your PPT, can you please tell your experience with Professor Bharati Bhatt in CARE, IIT Delhi?
Actually, I don't have much. I don't think I worked with Professor Bharati Bhatt. I have not met also, maybe. To be honest, maybe
there is one Professor Sharma. He was with maybe another Sharma.
I don't know. I did not work with Professor Bharati Bhatt, so my mistake.
Ito, you worked out, Professor Ito.
Yeah, I know very well Professor Ito. I think he passed away, last week. So I have met him multiple times. Of course, we worked on some steering committees also. So he's 100 miles from my place.
Yeah. So, dear participant, is it visible, sir?
Yeah, I can see my presentation. If you go to full screen presentation mode.
Right, sir.
But only thing now you have to run my slides, right? I cannot run slides, right?
Yes,
so
yes.
you'll. Okay, I think still not in the presentation mode.
Okay. So just a minute, sir. I'm doing it in a second.
Yeah, I think it is there now.
Right,
So,
sir. Right.
so we can start. I think you can. By the way, dear attendees, my coordinates are noted there, and the talk of the presentation. And I think Surajit informed about myself. So please skip that slide. Go to next slide, please. And so here, what you see is, if you go to previous, actually it went one slide ahead here. Here,
Yes.
I show some of the resources that I have in my lab, and certainly for performing hardware research, you need, experimental facility. So I have one far field chamber that goes 800 to 40 gigahertz, and then I have a mini compact range or millimeter wave chamber that covers 26.5 to 110 gigahertz range. In addition to other facilities, we can do 2D pattern, 3D pattern, gain measurement, axial ratio, sense of rotation. But what I cannot do in my lab is the antenna efficiency, just because I have to integrate full sphere, right? So of course we can do just that. It will be lots of time for the measurement. So that's the capability in my lab. So we can do something from 800 till 110 gigahertz and all the millimeter wave spectrum, which we can extend even to 220 gigahertz actually later on, if I can get some frequency standards. If you go to next slide, please. Over the years, we have worked on different projects, especially considering the funding situation and also based on the industry growth, starting from 3G to 4G to 5G. Very soon, people will be working on 6G, and then different defense applications are there. And now and then, if you see, frequency spectrum has been, being renamed from, let's say, for example, you have nowadays 5G new radio bands and R bands. Earlier, they used to be, other frequency nomenclature. So there has been lots of changes. Plus, the fabrication facility has come along, such as you used to have chemical etching, then we have 3D printing, then we have 3D metal printing, then we have metal stamping, nano fabrication. And if you are working on LTCC or STCC antennas, then you have, of course, some of those fabrications involved. So all these things have, accumulated over years, and different work experience has happened in my lab for the student those who have worked. Some may be very interesting, some may have come and gone in terms of technology, and we have to pick up the new technology. One of the new technology is that we are working is the flat panel phased arrays, and I'll be talking about that in this presentation today. And also MIMO antennas, people have worked, and we have worked a lot, just that I don't have time to cover in my talk today. So, but then my talk will focus basically on a year of work, or you can say 2019 to 2020 work, whatever we did in my lab, and some of those things. Please go to next slide. So 5G, since it's kind of a very hot topic, of course 6G is coming along, you need efficient antenna system to accommodate the data throughput requirement, as well as you need low profile antennas, you need low cost, or you need swap wise, right? Size, weight, aperture point of view. Frequencies can range from sub 6 gigahertz to 5G, 24 gigahertz to 28 gigahertz to 39 gigahertz, 5G bands to all the way millimeter wave spectrum. So lots going on that front also. You do need high gain antenna if you go to higher frequencies because of the propagation loss involved there. So reflector antennas, beam steering antennas, or multifunctional reconfigurable antennas, something that can be potential solutions. In this talk, I'll be focusing only on two kinds of antennas in the interest of time: offset reflector antenna, reflector antenna, and then phased array antennas. So both of them can provide you high gain. There is some noise there, Surajit. On your end, somebody has to mute. So thank you. So a reflector antenna can be, of course, can have its own. If you go to previous slide, please. It can have some advantages, some disadvantages. For example, it's bulky, 3D structure. But then the advantage is that you have, natural tapering there. So you have natural side lobe, control and cross polar control. If you have proper feed source and proper reflector design, it does have problem in terms of beam scan. You cannot get beam scan from a conventional parabolic reflectors. I will present some results today what can be done to get beam steering from reflector antenna. Of course, if you go to beam steering antennas such as phased array antennas, then they turn out to be, of course, they can give you high gain, but they're very costly. And then they can be low profile, but they have power dissipation problem, because then if you have RF components, they have heat dissipation. So how to handle that? So each of the solutions have some good, some bad, in it. And as we go during the talk, we can explore some of these things. Please go to next slide, and of course, next slide. One more, please. Here. So first, example I am giving is a W band feed reflector antenna solution, which we developed for CubeSat 6U CubeSat application. You may be aware that one U is 10 centimeter by 10 centimeter by 10 centimeter cubic volume. And if we have 6U satellite, basically it's treated as small satellite, or even nano to small satellite range. 3U, 6U, 9U kind of satellites are there, and they are being used for the on LEO Earth orbit to medium or Earth orbit, wherever you can close the link, mostly LEO orbit. So this antenna we developed, which has for the remote sensing application involved there, and we needed, since spectrum around 80 gigahertz, it still has, lots of, availability. So that was our focus, and then frequency goes high, so wavelength goes smaller. So you can still have around some 25 wavelength aperture in one U, or 10 centimeter by 10 centimeter by 10 centimeter area, an antenna there. So that was the reason to choose that, and it was done for Office of Naval Research here for their future programs. So if you go to next slide, please. So as a specific requirement was to develop something that can provide 200 megabits per second of data throughput, so they can take the picture from space and sent to the ground terminal here in San Diego in Point Loma. They have big Earth, station. And if you want to do that, as we go high gain, and if we want to consider the frequency, so the feed reflector is one of the solutions. The other solution is phased array solution. Again, I will talk in the phased array section there. Since one U space, the reflector antenna has to be very compact. So we chose F over D of 0.25 F over D. And if you want right-hand circular polarization from the reflector, your feed source should be left-hand circular polarization. And of course, such a F over D 0.25 design is very challenging, because your feed pattern has to be very broad. Cross pole, has to be controlled, and it does bring additional challenges. And yeah, so I will show you some experimental results on that. This work published in IEEE Transaction 2019 March, last year, last year, you can say now. So if you want to read more about it, please read later on, but please continue, go to the next slide. So since we need left-hand circular polarization from the feed source, you have to, have some kind of polarization mechanism. So we chose a dominant mode circular waveguide, And starting from port 1, let's say input signal is coming, or you can say a wave is coming there, and then port 2 where wave has to come out from the circular waveguide. And to generate the 90-degree phase shift property, because circular polarization means you need equal amplitude, 90-degree time phase difference, right? So to do that, we have a pair of 9 pair of holes in the waveguide, and this helps because you do not have to worry about any dielectric loss. People can do septum polarizers, right, and so many other techniques, but they turn out to be lossy, especially for W band. It will be very difficult even to build it. So here, simple waveguide with air holes. So we have not to worry about any dielectric losses. Efficiency is very good. Plus dimension is so small because wavelength is so high. So we have not to worry about, even if it is, 1 or 2 pairs of holes are more required, it is still very physically small structure. And if you see the slide picture there, I show you how to generate CP. So one direction, port 1, when wave comes as a conventional waveguide, one wave comes along the air holes. So therefore, we create 90-degree time phase, and the right-hand picture shows that how fields are rotating from 0 degree to 90 to 180 to 270 to give the circular polarization generation. And of course, some dimensions are noted, but that's something, just a number. Please go to next slide. While we have to build it for the, as a feed source, we have to also consider the, in effects coming from the reflector, since F4 is 0.25. So we wanted a symmetric ground skirt on the aperture of the feed, actually. That's why you see this, I don't think you can see my, cursor, right? So I have to depend only on explaining here. So your ground skirt balances the current, so which helps in equalizing the pattern quality. And of course, one can do electroforming, but that's very costly. So what we did is machining, but it's very high precision machining from custom microwave here in Colorado. We have a company that does most of the space designs. So it was machined in 2 pieces, and then with proper bolts, it was tightened to make one solid structure. And you see in the center the feed horn, and then the rightmost picture you see the reflector surface, which is a polished surface of 10 centimeter effective aperture. You go to next slide, please. So first we have to verify the feed source, and of course impedance matching is the easiest thing to look into that. And then since it is very wide band, something around 79 gigahertz to around 80.
Sir, your mic is off.
Sorry. So it got right now, or you missed some other thing? Okay, so I will just start from here. So first you have to have quality of axial ratio verification based on the theta and phi angle, right? So that's what I show on the right-hand pictures, where we have simulated and measured axial ratios, and it's a surface plot, or you can say contour plot. So we are looking the quality of axial ratio, or CP, over different theta and phi, not only at broadside angle. Many publications show only broadside, and that's not sufficient. So you can see something around 100-degree beam width we can maintain around 86 gigahertz, which is our design frequency for the deliverable point of view. Please go to next slide. So we also measured the pattern, the 3D pattern, and compared with simulated pattern, you can see that 3D pattern as well as 2D pattern, they all, they come very close to the simulations. And since it is feed horn, there is not much unknown if the proper build can happen. If it is microstrip or something, then you have many more unknowns to worry about. before you put it with the reflector, certainly you have to make sure you don't have any spillover, right? So the picture on the right hand shows that the feed is properly illuminating that reflector, and without have much worry about the spillover loss. So here we could maintain 10.5 dB half-edge illumination. Please go to next slide. We measured the pattern in chamber in the mini compact range that we have, and you can see that it provides something around 34.36 dB IC of the gain at 86 gigahertz. Cross pool is not so low. It's still very good for this kind of design because FOD is 0.25. If you can make a 40.6, then you can have another 20 dB suppression of cross pole. But in this case, since we're constrained with 1 U of satellite space, therefore, this is the trade-off in a sense you can see. And on the right hand, you see the measured 3D pattern actually, and shows the pencil beam. If you look at the gain versus antenna efficiency versus frequency plot, efficiency is more than 60%, and then of course gain around 86 gigahertz is something more than 34 dB, which was sufficient for us to close the link from space to the LEO Earth orbit to the ground terminal, leaving some 10 dB margin. So we'll always be closing the link. Go to next slide, please. You have to also do the effect of CubeSat chassis, right? Because if you have, and those are made of metal, so how they interact, and that's what is shown there. You can do that in ANSYS Savant or in TICRA GRASP, that they have implemented this feature now in last 2-3 years only. When we were doing this project, they did not have, and we had to depend on ANSYS, and then after that, they did fix it. So you can look at the chassis effect, and if you see the plot on the right-hand side, there is some effect from the chassis, but it's not a huge impact. So it verifies the response that we are expecting, and of course, we show that the work was funded from a Navy grant here. If you go to next slide. Go to next slide, please. Okay. Now something I will talk about 3D metal printing. I don't know how many of you are working with 3D metal printing. It has certain advantages. One of the advantages is low cost. You can make a structure in one piece. You have not to make if you do machining of a cylindrical waveguide structure, then you have to make in 2 pieces, and then you have to join with the proper bolts, screws, right? If it's 3D metal printing, you can do one piece, no such discontinuity problem to worry about. However, the problem is the surface roughness that you can gain with the machining, with the 3D metal printing quality that you have, plus the metal alloy they use. So in this design, it was done almost, of course, our work was done almost 2 years back. Paper came in April of 2020, which is last year. We use DMLS, or direct metal laser printing process, which is with the proper company, Protolab, not that I have this printed in my lab. And it uses aluminum alloy. I have heard in Germany there is a company which has better alloy actually, which can give better response than what I could get here, just for your information. It has the surface tolerance, as you said, in both X, Y direction versus G direction, and it depends on printer to printer. So in this case, the tolerance was 50 micrometer versus 125 micrometer for G axis. We did a K-band design, 26.5 to 40 gigahertz. We also have a polarizer, and we did build a V-band, dual circular polarized feed horn, but that did not work. And I will show you some machining-based result later on. If you go to next slide. So this is the picture on the top left. You see that you can see the surface is not so smooth, which is something since we so we have to factor in before we start printing it or we send it for fabrication. So we did the tolerance study of, along X, Y, and G axis to make sure how it impacts the radiation performance. And you can see the impedance matching is preserved almost, but as well as the radiation pattern. So there is some, some effect, but that's something not so drastic. And once we have verified this tolerance study or sensitivity study with the structure, that's when we were comfortable sending it for fabrication. At the end, you see the brass piece that is simply a K-connector based rectangular waveguide, coaxial to rectangular waveguide transition. And it's axial corrugated horn. It's not lateral. That's most of the time people use. As I said, this paper came in IEEE antenna propagation latest last year, so you can read more information. Go to next slide, please. This slide shows the experimental result, of course, in comparison to the simulations. Impedance matching certainly, is not the big parameter to worry. Then gain variation. And if you see around 37 gigahertz, I see some peak there, which is because I measured this in my far field chamber, which goes to 40 gigahertz. And therefore, we are kind of towards the end of the chamber, range, which makes some problem, or it may be also contributing to some surface roughness. So we couldn't determine that. If you look at the radiation pattern at 26.5, both for, since it is waveguide, you can define E plane and H plane easily done. It is microstrip patch, right? So in microstrip patch, prefer using phi 0, phi 90 kind of coordinate system, whereas in waveguide, you can depend on E and H plane if you have proper coordinate defined here. So in this case, you can see that the measurement cross pole is almost 10 dB higher than the simulated cross pole. And that is because of the surface roughness, which is happening from the 3D metal printing. You'll wonder the cost saving. So we got a quote for the same structure from machining. It was a couple of $1,000. Of course, that time around $2,000 something. And the 3D metal printing was only $400, which is almost $1,500 to $1,600 of saving. That means if you go 3D metal printing route, you can save lots of money, and at the same time, you can make one piece structure. That's the advantage, but at the cost of some of these, performance degradation, or you may say cross polar higher than the simulated. Go to next slide. We continue on this, and of course, since it was 26.5 to 40 gigahertz, horn, so 33 gigahertz and 40 gigahertz, we verified same thing, and you can see again cross poles are certainly 10 to 15 dB higher than the simulated ones. And again, we say it is the kind of the trade-off if you go the 3D metal printing route, which will change actually. Technology is going faster. In a year or two, you may see 3D metal printing, which may provide very close to smooth finish like in machining. And this problem may not be there in future versions of 3D metal printing. So I encourage you to do something like that if you are working on the feed horn reflector to use 3D metal printing. You go to next slide. We built a polarizer also, which also came in IEEE antenna wireless propagation latest December of 2019. Here it's very compact polarizer, and we have K connector based excitation. So structure is much more smaller physically. And once again, you need, if it is circular polarization, you need equal amplitude, 90-degree phase difference, right, to generate CP. So that's what the right-hand picture on top, you see that phase difference and amplitude difference. And amplitude is very close to 0 dB, not much variation, whereas phase does change plus minus 5 degree compared to 90 degrees. So that's the limitation. And since it has to be done with 3D metal printing, we have to again see the tolerance effect. And this was the first structure, then the feed horn. So that time we had a bit more tolerance problem than when we, and it was different fab house also. So their machine was 100 micrometer, and that's why we show that effect. Once again, we have to see the tolerance behavior, and since it is below 3 dB, that's when we said, okay, we can still build it, and hopefully it will turn out to be that way. If you go to next slide. In this case, the thing you notice that since we had both sides polarizer structure, it does offer some wide beam axial ratio performance in terms of theta and phi. Once again, do not depend on theta 0 or broadside angle axial ratio. That can be deceiving. You should look at other theta and other phi angles. Surajit, again, can you please mute? Surajit, can you please mute?
Yes, sir. Just a minute, I'm checking.
I think presentation was going fine, just that you have to mute. There was some noise, in background. So we cannot see the presentation now. Yeah, now it's back. Go to full screen again. Thank you. So you have to again look at the axial ratio over theta and phi angles, which we did, and over the frequency. And since it is wide enough, we measure this S parameter. And then if you go to next slide, then we measure the radiation pattern. Since it is simple open-ended waveguide, there is no horn or no profile attached to that. It has ringing effect. So what we measured the pattern in only plus minus 90 degree, and you can see the ripples are because of that. Had we had a choke or something, this was a smooth pattern. But then since our purpose was to verify the polarizer performance, especially with 3D metal printing, the limitations that we can see, and one thing you can see that axial ratio is varying between 1 and 3 dB. That means this is kind of border problem. If you are designing such thing, with 3D metal printing, basically you may end up also that your structure may not be below 3 dB axial ratio. So this is something as a caution that had we have done the same thing with CNC machining, it was much close performance than to simulation, and that's something we show from the result here. We go to next slide. Please go to next slide, please. Yeah. We also looked at some 5G solution with dual polarization, using again the circular polarization feature that I presented last slide, which was single polarization. Now we have dual polarization. You can have right-hand CP as well as left-hand CP, one for transmit, one for receive, but certainly it's not a star system. In a star system, you have simultaneous transmit receive. Here it is like half CDL, or you can have a frequency division duplex or time division duplex approach here. So you are transmitting at one frequency, receiving at other frequency, right? That's where, but we have dual pole, and they are coexisting, right, in the same horn there. To get the wide beam width, because that was something plus minus 30 to 50 degree in the single polarization structure here. Now with the corrugated teeth on that aperture, we could widen it to plus minus 60 degree range, which was sufficient for F/D 0.6 reflector. In this case, we generated 5 beams, although I will only be showing one beam result here, but our effort was to generate 5 multiple beams. And we verified the impedance matching as well as the axial ratio and gain of this feed horn. And you can see that with respect to simulations, they turned out to be very, very well. Of course, some variation. Again, this was again 3D metal printed. So since 3D metal printing, some surface roughness effect is still there. And one piece printing, just the benefit of 3D metal printing is one piece printing compared to the machining approach, and it's much, of course, lightweight also. If you go to next slide, please. So it's always good advice to verify the axial ratio versus different theta and phi angles. That's what we show on the left-hand plots for both port 1, port 2, which is one is right-hand, one is left-hand port. And you can see that they have wide axial ratio there. And we measured the pattern in the chamber for both port 1 and port 2, and you can see that they have good go and cross as expected. There's good agreement, and we had FORD of 0.6. In this case, we used spherical reflector because we wanted multiple beam generation. So if you have parabolic reflector, you will not get that. All the beams will still come out at the same location. So we use in this case a spherical reflector. And of course, 36 centimeter in that sense because we want 5 beams. And frequency was full 5G spectrum as per 5G new radio bands, 26.5 to 29.5 gigahertz. So I show one reflector response just for sake of verification, but this work is still some ongoing research, so I don't have all the information here. Please go to next slide. We did some millimeter wave or V-band additional, dual band feeds design. I had a postdoctoral fellow from China, Dr. Yu, and his student came, Ning Lau. So we did some work where we used one polarizer structure that shows like a sectoral shape there with some length L and some height with some angle information. It's not that polarizing structure we invented. It was something published in Microwave Theory and Techniques Society. Rather, we use that concept and to build it, for this frequency with dual polarization. Once again, when input signal comes at port 1, as it goes to the upper port, it gets the delay because of the sector there. So that's how you get amplitude and phase. So we showed the amplitude is around 3 dB, with some variation you can see, and then the phase is very close to plus minus 5 degree with 90 degree, means 85 to 95 degree phase range. So, and this one I showed the picture of the 3D metal printed, but did not work at this frequency. Simply those surface disruptors became killer. So we have to abandon that approach. Rather, we went to conventional machining, but not that very high machining, also kind of reasonable machining with but much more precision than the 3D metal printing. So, but again, we have to make it into 2 pieces, and picture shows that how we made 2 pieces, then we joined with the proper bolts, and how close you can connect, and you have to make sure there is no discontinuity. If not, that will be problematic in your design. And then this paper came in IEEE Antenna Wireless Propagation Letter, November of 2020, in a special issue, on millimeter wave antenna something, If you want to read more, you can get that information from there. We verified the impedance matching. Please go to previous slide. Impedance matching and axial ratio, of course, the radiation pattern, and they all turn out to be in reasonable agreement in this case. We go to next slide now. So you are going forward. Please go to here, one more forward. So now I will present some discussion on the phase array part, phase array antenna part. I think my time is also looks like only, 30 minutes left or 20 minutes left. So I have to be a bit speeding up. So once again, for the same CubeSat, we needed a solution where we have phase array component. So around 86 gigahertz, circular polarization, all those same specifications. If we go to next slide. So Jit, can you go to next slide, please? So we developed a butterfly rating element, which is something, a unique rating element. And then we use a series, our traveling wave antenna approach, our leaky wave antenna approach, where we have 16 or 24 or 32 in in series fashion. And people generally prefer 16, but then we have to see that is this sufficient? So if you see the current distribution, if you have 32 elements, the end element don't get any current, whereas the 1/24 has sufficient current. So 1/24 was our preferred choice, then 1/16 as conventional. To see how circular polarization happens, if we look at the bottom left figure there, where we have current rotation from 0 to 90 and 180 to 270, that verifies that how circular polarization happens. Simply, these butterfly elements are 4 small patches. They are properly rotated, and that's what gives the CP quality. This paper came in December 2020 IEEE transactions. Please download and read more about this work. But of course, we go next slide. I will talk more about performance. So we build of course, 8/24 as well as 32/24, because 8 by 24 was the first prototype, and then 32 by 24 to make sure we have enough gain to verify in terms of the closing the link. So you can see the performance, and you have to use 1 millimeter connector because you're operating at 86 gigahertz. And then it's not conventional SMA or K connector, just so that it is clear. Plus, it's a traveling wave antenna, so you have some squint problem. So you have to have some tolerance of 1 degree, 2 degree squint-based beam, bandwidth. So here we have 80.52 to 86.3 gigahertz bandwidth. That's where we want to operate. And if you see the radiation pattern for the 86 gigahertz, both Phi0, Phi90 for the along the 8 element or versus along the 24. So you have the beam narrower versus beam broader, that Phi0, Phi90 that you see there, right? And we did good verification based on the measurement. And then you see the axle ratio and the impedance match performance, on the bottom, left side, and you can see in the shaded area that it meets the specifications. And then we also verified the 32 element based design, which gave something around 24 dB gain. We did had more option to get the gain, but then we stopped there. If you go to next slide. We built the phased array counts, in this case also, as part of the project, we developed a 4-bit phase shifter with silicon germanium approach, and we bought some commercial low noise amplifiers. We built the prototype. By the time we tested, we noticed there was some mirroring happening. Mirroring means it's a multi-layer board. Some component were short-circuited. So we have to rebuild this structure before we can verify. But I will show you the simulated results for now. If you go to next slide. And this work you can get from IEEE Phased Array Symposium presentation more. If you go to next slide, please. You can scan plus minus 34 degree with this array and with a good Cohen cross separation. One thing to note, if it is phased array antenna, you have to look for active S parameter. Simple S parameter is not sufficient. And also you have to verify if active S parameter is in control as beam scans, as well as axial ratio. Since circular polarization, axial ratio is in control as beam scans. So that's what we show in the right-hand top and bottom figures. Active S parameter is maintained, as beam scans up to plus minus 34 degrees. And axial ratio is also below 3 dB. In the 85.2 to 86 gigahertz range area that we were shooting, even with the 28 degree beam scan. So the point to take from here is that active S parameter and axial ratio should be verified as beam scans, not only at broadside. That's not sufficient. Okay, if you go to next slide. We have done some flat panel phased arrays very recently. That's a very new emerging technology, where we can have very low profile phased array actually. We use RFICs, where we have if you see figure 1, what I say, so we have in one RFIC a few millimeter by few millimeter footprint. Both the LNA and HPA, basically it's a transceiver where you can, and it has 6-bit phase shifter, 6-bit amplitude control or gain control, and you have an RF switch that can toggle between transmit and receive options. Actually, these days you have one chip can feed 4 rating element. So there's a lot going on, and one company is the Anoki Wave, which we have used. Current phased array that I'm developing with is from analog devices, RFICs, but there are other companies like you see there, like Renaissance, RF Core, Mixcom. They have developed some chips. If you're working in this area, I will refer you to their company vendor websites and see what features they have in the RFIC. And this paper came in IEEE Access this 2020, I think October sometimes it came. If you want to read more, and this work was with my military, Navy, and Army collaborators. The challenge is not the aperture design, more is also the beamforming networks, challenge. It's a multi-layer board, 12 to 10 layer boards, and you can see the multi-layer PCB stack up. It's still 120 mil few millimeters only, but then each layers are few, 4 mil, 2 mil, 10 mil, and you have to have the power lines, you have to have the digital layer there, you have to have the vias going from top to bottom, and so this adds much more complexity. At this moment, if you want to use this for commercial, I will not recommend, because many companies have come and talked to me, but it is something on a prototype level. One project I have right now is for NASA, which I'm developing an array for 28 gigahertz for their lunar mission 2024, but then of course they have more money. So for commercial, I will say there is more chip prices has to go down and more fabrication has to mature. And the picture I show in the middle where we have some, how clean fabrication can happen. And you can use Altium software to create the board layout. If you go to next slide, please. So this is a photograph of a dual slant polarized, or you can say 45 degree and minus 45 or 45 135 degree. It's like for base station applications. You can transmit from both polarizations, and then of course this is the 5G frequency. So you can receive from a cell phone. Let's say, right, 5G. There are cell phones, smart cell phones with 5G capabilities. So that was the goal here, but as a prototype, we had a 8x8 array in this case only. We did also the over-air testing for this aperture to see how much data throughput we can handle. And the setup is shown in the bottom, right, bottom left, section there. If you go to next slide. I have to be past a little bit in time, so don't spend, but you can ask question later on. We verified this array in my chamber, and you can see the beam steering can happen even all the way till 70 degrees. But you have to note when you do the phase array designs how much gain drop happens in the scanned volume. That's the figure of merit. So broadside to, let's say, 60 degree, and you have got 4 dB gain drop. So is this acceptable? That's something should be noted. So in this case, you can see that we have sufficient, good, I will say 3 to 4 dB gain drop only from broadside edge beam scan, 28, 26, and 30 gigahertz. One of the problems we notice is very hard to determine the actual gain of the array because you have RF components, LNAs, HPAs, and phase shifters. Very hard to de-embed the losses or the active component compared to the passive array gain. So we did try that effect. That's what we show in the gain versus the frequency plot there with certain uncertainty because it's kind of estimation here. But then you can do it, but it's a very hard approach. So if you are doing something like that, I caution you to be very careful in your measurement process. If you go to the next slide. If you go to the next slide, please. Okay, so we did the data throughput testing. Of course, based on the instrumentation we had, we only did something with 64 QAM, but you do need signal generators, you need a spectrum analyzer, you need some frequency convergers. Of course, in this case, we used a NUC-Wave 0170 mixer to up convert and down convert. Both on the transmit, we had a 15 dB gain horn and the receive. And now what we designed, and then we swapped it to make sure it works either way. And some of this setup information is in the IEEE access paper that I mentioned. If in case you are doing something, please refer that. And this was done in the Navy lab here. Not in my lab, so they have more instrumentation than I have in my lab. If you go to next slide, please. Here we demonstrate the comparison of 16 QAM versus 64 QAM, data throughput testing, and what you see is the error vector magnitude.
Sir, audio problem.
Somehow it gets muted. I'm sorry. Please go ahead again to the slide. I think somehow it gets, muted. I do not see presentation, so you have to go back to presentation. Yeah, thank you. If you go to next slide, please. So in the interest of time. Okay, so we also did some dual circular polarization design where we have again same flat panel phased array, again very few millimeter thick with unocave RFICs, and we verified both right-hand CP and left-hand CP performance. You can see the RFIC is shown there in the top, inset picture there. Again, one chip can feed 4 rating elements, so that's the beauty of the chips and very low profile and not much heat also, because generally phased arrays have the heat sink problem, but chips are here, they have designed such a way not much heat is being developed. If you go to next slide. Please move on to next slide. Yeah, so we did some reflector-based beam steering. I don't know how many of you know that if you want to use reflector for beam steering, parabolic reflector is no way you can get anything. If you try that, that's what you will see in the picture that you see on the left side. Your beam will scan, but your gain will drop, and that's something you can do it by having lateral displacement of the feed. And it's not acceptable from phased array or beam steering antenna point of view. So what we did in this approach, we used a phased array antenna as a feed source. And then we used a cylindrical reflector to steer the beam. And so that you are plus minus 3 dB gain drop range. And we again used the flat panel phased array feed source design. It was done for Navy for there's some future applications. If you go to next slide. Can you go to next slide, please? Yeah. So here you see the cylindrical reflector and the arrangement with respect to feed source in the before you start doing something. Of course, you have to have conceptual design, and you can see that along the cylinder axis you can steer the beam. Along the parabola you cannot, right? So we show with the line source. As a feed, and we did the MATLAB-based calculation to see if the concept works before we go to TIGRA or any software or you build anything. And you can see that in the on the right-hand side we have the beam at the center versus beam at the edge. Since the reflector was set to 50 centimeter only because of the Navy restrictions, they did not want big enough structure because of aerodynamic problems. So had we had larger dimensions, 75 centimeter, 100 centimeter, then we could have scanned much farther. And of course, you can see here there is some spillover happening because the dimension was very restricted. Again, it was very low FOD design also. If you go to next slide. So there is a delay, but yeah, so what we did in this case, we have a simple stacked patch because we wanted to get the half CDL frequency range and with proper port to port isolation, and so 4x8 array was chosen because that's what was sufficient to illuminate the reflector surface. And the tops you show the aperture, and the bottom you show the RFICs with and the beamforming network will be in between layers, that multi-layer board that we have. One thing I did not mention, to control the beam steering, you need SPI control and with the microcontroller. And that's the black piece with the wire that you show there on the top section there where we connect microcontroller, and that's something these chips allow. And of course you can buy from National Instruments some of those component through you can do the programming and develop the GUI for it. Like this chip that we are using has some 28 dB receive gain, 20 dB transmit gain, and of course it has a 6 dB phase control and gain control. And it's a wafer level packaging of the chip, 2.5 millimeter by 2.5 millimeters. So you can see these are so small chips and can feed so many rating elements. In this case, of course, this chip was per rating element one chip. If you go to next slide, that's a KU band design. So you develop the array, then we have to do thermal testing because if it is heat sink problem, so we did temperature measurement. It is something around 84, 58 degrees with the infrared cameras, and it has some 6.3 watt of power dissipation. We verified the the phased ray 4x8 array performance alone first, both for the X polarization and the Y polarization. And with the beam steering, that what you see simulation versus measurement comparison, and they are very close. And of course, if you have done proper designs, not much to worry. Other than the cross polars, you can see cross poles are slightly higher in the measurement than the simulation, which may be also because of the chamber, the noise floor. Go to next slide. So then we have to verify the reflector performance. We have TICRA grasp to do that. You can use HFSS, physical optics, or CST, FICO, other tools also. They all have these asymptotic methods these days. And we verified the beam steering, which simply phased ray is feeding reflector. So therefore, reflector is beam steering is coming based on the phased ray beam steering response. Previous slide, you saw the phased ray performance. Now it is the reflector beam steering performance. And if you go to next slide, just a computation-based verification. If you go to next slide, we show the experimental verification in the in the compact range. Not in my lab, rather it's a Navy lab measurement because they had bigger chamber than mine. And the reflector, you can see the feed phase dish is located there, and it's a metal stomp reflector, aluminum material based, and it has some metals, surface flush mount bolts only to hold the mount with that. As a 3D metal, 3D dielectric printed mount, and the phase ray and the aluminum based reflector surface. And you can see for both polarizations, we had beam steering in plus minus 30 degrees as you expected. You cannot measure gain, as I said, because of the active components. You have gain, but just very hard to say that what actual gain is. So we depend upon the either you do the calibration based estimation, or you just say that you look at the beam width in this case. And that's what we did. And this paper came in IEEE Antenna Wireless and Open Journal of Antenna Propagation, 2020 last year in January, February sometimes. We go to next slide. So I think after this talk, I will, in a few minutes, I will close my talk here. I know I don't want to take much time from you guys. So we did also some multifunctional, designs for 28 gigahertz 5G band using the same butterfly or traveling wave antenna category. But here, one antenna can, since it is multifunctional, what we are doing, we are getting the beam steering, we are getting the polarization reconfiguration, we are also controlling the beam width in one array. And of course, I will show you how, in this, few minutes from now. And this paper is still in consideration for IEEE transaction, minor revision, so should be accepted very soon. And you will see, hopefully, if you want to read more about it. If you go to next slide. So here we used, staggered butterfly rating elements so that we can arrange them, all the rating elements. We have out on dummy linear arrays, both top and bottom, because you want to get mutual coupling in control, right? So otherwise you'll have, some issues there. So you need dummy, elements there. That's what we have here, and those are matched terminated elements basically. Those are not excited. Our remaining ones, 8 in the center, those are the ones which are fed. And we can get both right-hand CP, left-hand CP, linear X, linear Y. So if you are feeding from both sides, then you can get linear X or linear Y. If you are feeding only from right-hand side or left-hand side, you can get one of the circular polarizations. If you go to next slide. So this is the fabricated antenna, photograph, and that has the rating elements with the proper, feed where you have K connectors there, and what you see is the K connectors with the matched terminations there, except the one we are trying to test where we have the opening there, and it has analog devices RFIC. ADMV4821, which we used here. It's like the same flat panel phase drift beamforming network I was showing. The chip has the property to where you can vary the amplitude phase, and you can get whatever 5 responses you want from one array. And of course, aperture has to be there, plus the beamforming network has to play the role there. So if you go to next slide, I will show some performance. So we measured the impedance matching, of course, for both simulated versus measurement. You can see that they are in good agreement. And then axial ratio verification for the right-hand CP and left-hand CP verification within the, again, these are all traveling wave antennas, so they have a squint-free bandwidth there. In this case, our goal was 27.5 to 28.3, so it is sufficient for 5G band with plus minus 2 degree beam, beam squint, range there. We go to next slide. And here we show the comparison of the 4 circular 4 polarizations, right hand, left hand, linear X, linear Y with simulation and measurement. You can see they are in good agreement. I just said by feeding right hand side of the array or left hand side of the array, you can have one sense of rotation CP. Then if you feed from both sides, that's when you have the linear X or linear Y based on the amplitude phase combination that you have. If you go to next slide. We did verify the beam steering response also. Since you have a phase shift information in the chip there, you can apply the progressive phase shift, you can steer the beam, and you can see you can get here plus minus 50 degree beam scan, with some 3 to 4 dB gain drop. The most important thing that is the flexible radiation pattern. Basically, if you can excite one of those, series fed arrays in the whole array if you want, because your feed network is active, and with the SPI control, you can tell where the signal should go, where the power should go. So that's what we do here, and these are all measured response, by the way. So by having only one branch or 7 branches, are all branches, and you can see as the number of branches increases, directivity increases, right? And this is something you can do to close the link, right? If you are close or if you're far, and therefore you can tailor the amount of gain and the coverage that you want from this array. On the right hand bottom, I showed the peak realized gain versus frequency for the CP, and linear polarization cases, and they turn out to be very good. If you go to next slide. Please go to next slide. Some advertisement. I don't know if you have seen some books that I, co-edited along with my advisor from Manitoba, Lashify, as well as Dr. Sudhakar Rao from Northrop Grumman about feed reflectors. Those who are in satellite industry, I'm sure you may have seen these books, and lots of good information in that. We go to next slide. Go to next slide, please. This is my new book that is coming from IEEE Press and Wiley about multifunctional antenna generation. It should be by April, second week. I think it went one slide forward. If you go to one slide back, please. It went one slide forward. Can you go back one slide? Yeah. So it has some information on different chapters, different kind of antennas that we have discussed in that in the book there. I think if you are working on 5G, massive MIMO kind of approach, reconfigurable antennas may be a very good handy book for you to read and learn more about it. And of course, I have some picture of my dog and my cat, so who are my prince and princess. We go to next slide. Next slide, please. So I think while Surjit is going to the next slide, which is the last slide, I will say that I'm done with the presentation. I will entertain questions. If you have anything, please don't hesitate to ask. I will try to answer as much as I can. As I said, I presented some two basic antenna types, reflector and phased arrays, which I think are very valid from today's satellite communication, wireless communication point of view. And we do other research, as I said in the beginning, but then certainly if you have any question, feel free to ask. Surajit, any question?
Sir, what is the difference between active S parameter and S parameter?
Active S parameter takes the mutual coupling effect, whereas simple S parameter is only standalone. Let's say you have 4 port, right? You are measuring S11, S22, S33, S44. Whereas active S parameter will take care of mutual coupling effect. For example, in a phased array antenna, let's say you have 4x4 array. Then you can mass terminate all other rating elements and you can excite only one element there. So it will have the interaction of the neighboring elements. That's what is the active S parameter. And so if you do with the phased array design, make sure you take care of the active S parameter measurement as beam steers, as beam scans. If not, you'll have the situation that beam is steered, but then you have very poor active S parameter, means your gain will drop. Okay? Any other question?
Yes, sir. In the chat box, I could see a lots of questions and appreciation messages. So, can I read it, sir?
Yes, please. Yes, please. I cannot see
one by one
the
questions.
Go ahead.
Okay. Yeah, Professor Mahadevan asked that at Ka-band component size being small, it may be worth going for conventional matching. Axial ratio of 3 dB may not be acceptable in many applications. Your views, please.
Yes, you are right. So if we are doing low cost fabrication, right, that's why I did the 3D metal printing. If I do the machining, then I can get what I'm expecting close to 1 dB axial ratio. It's just that we wanted to see how 3D metal printing, comes handy. And also it's one piece fabrication. So simply we are trying to see the benefit of the 3D metal printing in that case. Otherwise, I completely agree. And that's why if you see one design I presented in the beginning for W band, when I had the feeds horn, where axial ratio is below 1 dB over the 10 gigahertz bandwidth. So yes, you are right. If you want to do the satellite application, then certainly if the performance is the requirement, then you cannot depend on 3D metal printing at this moment. You have to go back to very high quality machining or electroforming or something else. You're right.
Thank you.
Any other question? Any other question?
So, in case of a chip which you use it for a polarizer, okay. So the polarizer, that chip type of polarizer will be very lossy. So can you really tolerate that?
Actually, those chips also come with 28 dB LNA, 20 dB transmit chain gain, right? So even though phase shifters will have losses, even though you are right, phase shifters may have their own losses, right? And switches may have own losses, but you compensate from those LNA and HPA gain. So you end up getting more than what you could have got with the passive design.
So your LNA, your amplifier inside takes care of that, all the losses.
Yes. If it
but
is
that will involve a lot of DC power.
Yeah, you need DC power, but certainly I'm designing this technology-based phased array for NASA, for their 2024 lunar mission actually, and they are depending on the solar-based generation only. So you can see if they can use it, right? So it's not that bad. It's just that you have to budget in your, make sure that you have enough solar energy, or if you are on the ground on Earth terminal, you have enough battery power. Yes, there is some DC power required. It's for any phased array antenna, right? They all have all active components. Yep, these are conventional problems.
Yeah, that is true. So they have to make sure that sufficient power is available for even the polarizer which you are using it. See, normally it is taken for granted that the polarizers are all passive.
Again, yes, you have to make sure that you have enough power, right? If not, you'll not be able to close the link. That's why first thing you do, do the budget link calculation. See that are you having, and you have at least 10, 15 dB margin, because it may end up getting some less, right? So you have to have some margin. So yes, you have to be careful about, or you have to be worrying about how much DC power you need. And I think reflector performance is still better than phased array, but only thing, reflectors will need gimbal, right, to have beam steering, because they are mechanically steered structure, except the one I presented with the cylindrical reflector where I can do beam steering, but then still I need phased array and I still need the, DC power and all the thermal issues to worry about, but these are very high quality chips, so it's not same problem. The problem is the cost. The chip prices are very high even now. So for commercial purposes, I don't think they are ready. Just that in few years, you will see them.
Yeah, that's true. Any chip which is in small quantity will be very expensive, no doubt.
Very expensive. I just bought $20,000 chips, 500 pieces of $20,000 chip only, for this NASA project. So you can see that there is lots of cost there.
Yeah, that is true. That's true. Okay.
Plus one board bill is $15,000. Yeah, go ahead.
A compact range which you have in your lab, which is from 100 up to 100 GC. Okay, but that houses reflector of what size?
I don't recall on top of my head. I think it is 60 centimeter offset reflector.
Oh, I see.
I may be wrong there. It was 3-4 years back we installed it, so with MBG. So
I see. So that reflector surface accuracy is good enough to go up to 200 GC?
Yes, because that came from MVG. It's professionally done, right? So it is exactly, they qualify till 220 gigahertz. If I can buy frequency extenders, I can go till to 220 gigahertz.
Yeah, that's how normally they build the compact test range, so that the reflector is the one which you cannot replace every day.
Exactly.
There's other things we can do. Okay.
And they have rolled edge, right? They have rolled edge also to take care of the
rolled edge for taking care of the serrations are done, etc.
Yep. So, you're right. You are right.
Thank you very much for the interaction.
Welcome. Any other question?
Yes, sir. Yeah. Thank you, Madhavan sir and Professor Sharma. We are having a couple of further questions. Anjan Bandhapadhyay asked that, how do you measure circular polarization in your lab?
Good. So we have in our lab, of course, it's a far field chamber, and we have Orbit FR software that comes with the measurement system, and it can do the one way for measuring circular polarization is the rotating linear, right? Where you can see the magnitude of the field variation and you can say how much acceleration is happening. But in my chamber, we have the capability not only to measure the sense of rotation plus acceleration both. So the software takes care of that. Simply you measure E plane and H plane, and it takes care of through the processing of the software, and of course you have to see that you have to measure at different phi and different theta angle to make sure over the space, it is giving the CP quality. So simply you have to repeat measurement at different phi angles. So I showed some contour plots, measure contour plots for that. It just takes lots of measurement time, but software provides, that information, not only the acceleration, also sense of rotation. And you can get it. They charge another $10,000 of additional cost on that, but the something is very valuable.
Yes, sir. Yeah. Ganga Shagar Bharma asked that, can we amplify desert lobe of antenna pattern?
You can amplify, but why you'll, amplifying is in terms of signal to noise ratio. Look at that, right? I don't know if you're right in the question or I'm right in the answering here. If you amplify something, right, what happens? Your noise floor also get amplified. So signal to noise ratio is not, at the effect is not as a benefit for you. So if you want to,
sir, I think he is asking about the radiation enhancement, because he is saying that the amplified design.
LNAs are only the power, right? Pattern is independent of radiation. Pattern is independent of the power, right? when we do the directivity or gain or the pattern, they are all in terms of, they are all are independent, right? They are, so there is no such term. Only thing you verify the pattern. As far as gain, yes, you have more gain now because LNA is spitting more power, right? Or if it is, sorry, when you are receiving, and when you are transmitting, HP is spitting more power. So you get more signal strength. But the pattern will be same. Just the signal level will be up and down based on the LNA HP information, right?
Yes, sir. Obhinav Roy is asking, can we use microstrip reflector array antenna for the CubeSat communications?
Yeah, you can use. People have done that actually, you know, in JPL and also in UCLA, they have done something like that. Yeah, you can use it. Rather, they have been doing for all SAR applications, for weather radar forecasting applications. So yeah, you can use that. It's just that reflector array design with the feed source and the, you know, and of course, if you all based on where you are launching, right? Is it a space application or ground application? So you have to be careful of. But yes, it can be used, of course. Bandwidth may be a constraint because microstrip may have some bandwidth limitations, right? Plus any other issue that comes with the microstrip problems.
So, sir, one question quite often that comes in my mind, and that is, sir, whenever we are using some patch antenna, so whenever we are designing some patch antenna, so as per the simulation results, we are getting that it is working very perfectly, maybe till 20 gigahertz or beyond. But whenever we are doing measuring beyond 10 gigahertz, you are not getting the actual results as per the simulation. Always the results are used to get deteriorated. So, what could be the reason for that? Especially for FR4 substrate, we have seen that.
Yeah, so FR4 is very bad material. Beyond 2 gigahertz, I will never recommend that. Even 2 gigahertz, if you use the FR4 last tangent, is very humongous. Actually, if you all based on from who you are buying FR4 material, they have last tangent of 0.02 to 0.06 range. And then, of course, the material gets dispersive. So beyond certain gigahertz, you have the lots of loss, dielectric loss, and you know, attached there. So therefore, your gain drops. It's not that your antenna is not performing. It's just that you have losses there. So I will never recommend using a FR4 beyond 2 gigahertz. Use a high quality Rajas material, or if you have to use 4.5, use AD450, which is now a Rajas material also, which is low loss tangent 0.002 or something. So I will not recommend using a FR4 beyond 2 gigahertz actually. I even beyond 2.4, I will say stop it.
Right, sir.
Okay.
And yes, sir, very correct. So thank you, sir, for this very informative session, and for almost covering all the foundation and applications of millimeter wave high gain antennas, array antennas, and also you have gave your insight on CubeSat antennas. So thank you, sir, for this very wonderful lecture.
Thank you. Thank you.
It's a pleasure to attend you, sir.
Thanks
so
for
the dear participants, yeah. Yes, sir.
Thanks for inviting me. And if anybody has any question, and
Yes,
I don't know if I can respond all the emails, but if something important, I will try to. If something valuable, of course, I will try to respond to you based on my time. But feel free to let me know.
Yes, sir.
Okay.
Thank you, sir.
And I do apologize for any technical issues in the beginning of presentation. So I hope you all enjoyed, and you all have a nice day, and take care. Stay safe. Bye.
Thank you. Bye, sir. Bye. Thank you, sir. Bye.
Take care.
Yeah. Thank you, sir. So the participants will be having the next technical session from 2 p.m. Indian Standard Time. That session will be taken by Professor Raudra Ghatak from NIT Durgapur. And I could see that questions regarding the sharing of PPTs and other things. Previously also I mentioned that I will ask to the respected resource persons to share their presentations, like Professor Sharma shared. If others will be sharing, then I will mail it to all the attendees. Okay, after completion of the workshop, not now. Sure.